Hello everyone. In this video we are going to implement a project for our course. This project will tell us how to implement the IR receiver emitter using the FPGA board. So we will go through the project with some steps to learn how to implement it on the FPGA board, and then we're gonna test the design by using a timing analyzer tool and chip planner tool. So our first part will be creating a project. So we'll go like to click next, choose a folder to work on it. So go to the download and call it homework number 4 for our design. And let me give it a name called IR. Then I will click on select folder. So in this part here, in the name of the project, we should give it the same exact name as we have it here in the file, in the source file that provided to us from the professor. So I'm going to pick the same exact name, and then I'll click next. We'll keep this folder as empty, and we'll not add this file yet. And click next, choose the family for our FPGA device, and I'm going to go with DE1-SoC family, which has the device name as here, and I'll copy it, then paste it in the name filter because there's a lot of families name here. I'll make sure that it's the exact one. Okay, then I'll click next. We don't need to use any EDA tools right now for this project, so I'm gonna click next and summarize all the information that we have here, and then I'll click finish. All right. So now it's creating the project for us. Our next step will be copying all the files that we have here to the exact location of the folder that we just created. So I'm going to take all the 4 VHDL files, Verilog files, sorry, the SDC file as well, and I'll keep the QSF file for later. So I'll copy these files and go to download and paste them here. All right. Okay, so we are in good condition right now. Let me add them to the device. As we can see here, there's no files that have been added to the project. So I'll go to project and remove files, and I will pick these all files. No, I will need to see all of them. So I will just choose all the 4 Verilog files in addition to the SDC file. All right, good. So I'll add them. Now all of them has been added to the design, as you can see here. Okay, Verilog, and type. This is the synopsis design constraint file that we need for applying. So I'll click on apply or okay. So as we can see here, all of them are added to the design. Our next step will be editing the QSF file for our design. So as we can see here, this is the QSF file for our project. It's totally empty. There's no assigning for any pin assignment for it. The reason we are doing this is because we sometimes have a lot of numbers of pins, so it will be hard for us to assign all of them by using the pin planner or that we used to do in all projects. So I'll go here. I will just copy the entire QSF file. As you can see here, it has all the pin assignment and different things. So Control A, click, right click, copy, and go to this one. I will just delete all the info that we have here. Okay, Control V. So I think we just did it in the right way. Okay, cool. Then I'll click save. I will save all that work. So it's going good. So for now, and there is another way we can do it for it, but it will be very hard and difficult for us. All right. So right now we have imported all the Verilog files, SDC file, and the the QSF file. I will compile the design then. And wait for it until we finish. And I'll come back again. So, alright, right now it's 99% of compiling design. After we finish this and we have like 100%, we will go to the timing analysis. So here, time quest, double click on it. Right now we have this window here. We are going to see the critical path and the timing, the maximum frequency that the design is working on. We go to datasheet, reports, Fmax here, summary. It's compiling it. So as we can see here, the restricted maximum frequency for our design, it's 170.1 megahertz. So this is the maximum frequency that the circuit works on. Our next part will go to find the 5 longest critical path that we have for the design as requested from us from the professor. So I will go to custom reports, choosing reports timing, and here report number of paths. We already have it as 5, and then I think that's good. We don't have anything else to do. So after that, I'll go to report. Alright, so this way. So as we can see here, we have here all the 5 longest critical paths that we have for the IR transmitter receiver design that we have implemented. And as we can see here, the slag is in positive. That means that our design is met for the design constraint. Timing file and everything is fine. As we can see here, it's 14.1 nanosecond and it's green, so like we are in good condition. So, and the delay, data delay for each path is from 5.6 nanometer to 5.5 nanometer. Good. So this is what we get from the timing analyzer tool. So if we want to go to the chip planner to see this critical path, the first one, I will right click on it and then go to locate path and locate in chip planner. This technology will give us the critical path for the FPGA circuit, the design, and to give us like a visualizing thing to see how the circuit is act. So as we can see here, if we zoom in, just right click on the design itself, we can see this is the critical path for our design. It goes from this lookup table here, then go here, take this direction till it finishes here, then we go here. So it goes from this design to this design. So our next part will be changing the path for the critical path and move the lookup tables like for the top left side and for the right left side. So I will just move the editing mode from equal to assign, and I'll go this with this lookup table, take it to the top left right of the design, and I will go with this one and take it to the left right of the design, and we will notice how that will affect the delay of the circuit. So after we finish this, I will close the circuit here and compile the design again, and we will notice the difference. I'll close this. So as we can see here, that just to mention something else to the design. If we want to change the slack and make it negative and violate the constraint time that we have here, the only thing is we need by changing the constraint files here, and instead of making it like 20 nanosecond, I will make like 2 without needing to compile the design, because this is just an input file for the circuit. and we can see the effect on it. So right now I will not change it. I'll keep it as it is, and I will compile the design, and we'll see notice the delay, the effect of the delay that happened to our system. So I will click on start compilation, and I'll come back again once this will finish. So right now we are like 99% for compiling the design. I think everything will be good. So first thing I will change the clock from 20 nanosecond to 2 nanosecond to see just the violation that we make to the circuit. Alright, then I'll save this change. If I go to the timing analyzer circuit, go to the timing. Alright, click like 5 longest path. Okay, so as we can see here, it converts from black color to red color. That means we have violated the constraint file, the maximum clock frequency that the design is working on, and as we can see here, the delay and the slack has been changed from positive to negative, which is not a good thing. That's why I'm gonna go and change it to its real values. All right, I'll close this. And save the changes that we have made. Go again to the design, to the timing analysis. So we go to the report timing again. Choose longest 5 critical paths that we have for the design, and there we go. Actually, if we can notice that when we change the location of the lookup tables on the FPGA, the delay has been increased from 5.6 nanosecond to 9.6 nanosecond, down approximately to 8.7. That means we have been changed and we have been added so much delay because of the wires are so long. For that, to notice that, we can go here and see the location on the chip planner for the moved cell. All right. So that's what we got here. If you can see let me close this one and make it bigger. All right. So this is the critical path. As you can see, this is all the delay that we have to the circuit from the right, top left, sorry, to the bottom left, as we can see here. So this is the longest path for the circuit, which means, and if we go further, the design, location of the assignment, we will notice that 2 assignments have been added to the design, which is the IR transmitter for the counter and for the IR, and each of them has these dimensions for X, Y, X, Y. So yeah, that's it. So this is what we get from the chip planner after we change the position of the lookup tables, and it's proof for us that once we make the design wider, that will add more delays because of the wires to the design, and we will not be able to reduce the delay for the circuit. So to make the delay less, we need to combine all these block tables together, lookup tables, and make them in a small area or small place to see what is the delay. So I think for this part we have done it, and we're going to move to the second part of the project, which is taking the SOF file, the stream file, and copy it, paste it to the patch file. All right. So as we can see here, we save the design in the download folder, and I will go and take the SOR file from the design, which is here, DE1-SoC IR-SOR. I'll take a copy of it and go to the source file that we have here, source IR, demo patch, and I will paste the file. Alright. So our next step will be working on the FPGA board. So I already turned it on and it's working right now. So after that, I will run the FPGA board in a new way, not the exact way that we used to use when we have the programmer. So this way is very easy, will make us to run the device, run the FPGA board after we upload and bring the SOR file, the stream file to it. So I'm going to run as administrator and see the effect on it. Yes. Sorry for that sound. So now it's uploading. And as we can see here, we successfully run the device and it's working perfectly. And the total information, as we can see, it appeared here. And for the FPGA board, it's working perfectly as well. And if we change the values for the switches from zeros to ones, we can see the effect and how it works on it. So actually, this is the project we are creating right now, the IR transmitter receiver on hardware, and we tested on the timing analysis tool, we chip planner, we made all these changes on it. Then we took the SOR file and uploaded to the design by using a new approach, which is the patch file that we have it here. And as we can see it here in the project for the final design. And thank you so much.